Good evening, everyone.
Good evening, sir.
Good evening, sir.
કોણ છે આ લીટા કરવા વાળું? એ તો હમણાં બંધ કર્યું. ચલો હવે સ્ટાર્ટ કરી દે, એટલા તો આવી ગયા છે. ઓકે, so this is chapter 2, right? This chapter 2 is about potential, right? Electric potential or electrostatic potential, and then the last part of the chapter is about something called capacitor, right? Okay, intense you studied about resistors, right? They are used in circuits, right? Similarly, capacitors are also a kind of instrument or device that is used to store energy, right, in circuits. Okay, so first of all, we'll start with potential energy, right? So potential energy, right? See, we have already studied many different kinds of potential energy. For example, gravitational potential energy, right? We figured it out finally that it is equal to gmm by r, right? Okay, we have also studied potential energy of a spring like half kx squared. Okay, so there are many different kinds of potential energy. In this chapter, we are going to talk about potential energy for Coulombian force, right? That is electrostatic force, right? Now see, let me tell you beforehand, before we go to anything, right? Force of gravitation was attractive force, and it was equal to, in magnitude, in vector form, it was equal to minus g m1 m2 by r12 square r12 hat. If you compare that with Coulombian force, right, means electrostatic force, right, Coulomb's law, it is F vector equal to g m1 m2 upon r1, k q1 q2 upon r12 square r12 hat. So a basic difference between these two forces is that gravitational force is always attractive, right? But Coulombian force may be repulsive or may be attractive, right? So what happens is here, the potential energy in gravitation turned out to be minus g m1 m2 by r. I hope everyone remembers that. Okay. So we expect that in Coulombian force, the potential energy will turn out to be k q1 q2 by r12, will not have that minus sign. That's it, right? So in fact, this is absolutely true, right? This is absolutely true. That is what you get ultimately. But we are going to derive it formally, doing all the steps. All right, so let's begin. Right. First of all, we'll deal with easy case. Very simple, straightforward case. Suppose there is some random kind of electric field, okay, right, in this space. Okay, so we've got some electric field E in this space, right? And here let's say that there is a charge, okay, positive, let's assume it is positive. So this positive charge, we want to move this positive charge from the point A, it is here at point A, and we want to move it to this point, that is we want to move it right from here to there. Okay, so obviously this positive charge is going to experience a force, right? So that is called the electric force, right? This electric field is going to apply a force on that, and that force is going to be QE vector, right? So now if you want to move it, if you want to move this charge, then of course you have to apply force, because if you don't apply force, this charge will run away like this in the right hand direction because of the force of electric field. So to make it go over there, to make it move from A to B, let's say we apply some force and we call that force external force. All right, see, this field and charge together make system, and we are external. All right, so we are applying that force. Okay, we are applying that force. Priyansh, if you have a question, you could type it. Right, we are applying this external force so that this charge will move from this point A to the point B. But we apply F external such that the charge or the particle does not gain kinetic energy. That is that is we move it, we allow, or we have the force such that it moves very slowly with negligible velocity and acceleration, right? Okay, I don't know, Priyansh, what have you said? એક સ્લાઇડ નું લખવાનું રહી ગયું એટલે કઈ ખબર ન પડી. Okay, so what I'm saying is that this particular charge is to move from A to B, but we don't want it to gain or increase kinetic energy, right? So we are going to apply F external such that it moves very slowly without increase in velocity or without acceleration. So that is only going to happen, right? When can something have zero, or when can something have zero acceleration? If the total force on it is equal to zero, right? Okay, so don't worry, Priyansh, I will show it to you at the end, right? At that time you could write it. Okay, so acceleration is zero, so sigma f should be equal to zero. All right, so now if sigma f is equal to zero, that would mean f e vector plus f external vector should be equal to zero, right? Okay, because two forces are acting on it, one is electric force and the other is one that we are applying. So finally that will give me f external equal to minus fe. All right, okay, right? So now if I want to know, see, we were applying this force on this particle, we were applying a force like this, F external, and we made it move, right? We made it move. So obviously there was a force, and there was also a displacement from A to B, right? There was a force and there was a displacement from A to B. Now whenever there are both such things, there is likely to be work. So work done by external force, right? The one that we are applying. So obviously there's a force and there's a displacement. So there is work done by the external force, right? So W external. Okay, this is W external, or work done in going from the point A to the point B, right? The work done by the external force while taking the charge from A to B in a very slow manner, right? Without acceleration, okay, with negligible velocity, with negligible velocity. All right. Okay, so how much is this work equal to? Well, I'm sure you understand that the basic definition of work is as follows, right? Work is nothing but integration of f vector dot dr. From which point to which point? From the point A to the point B, right? From the point A to the point B, right? But now, if I use this relation in this formula or in this equation that I've got, this will give me W external in going from A to B slowly, of course, is equal to integration from A to B minus F E vector dot dr, correct? Okay, right? So now think about what is work. Work is nothing but transfer of energy, right? Work is nothing but transfer of energy. Clear? So we did work. The external force did some work. Where did that energy go? Think about it. Answer it in the chat box. Come on. Where did that energy go? We did some work. So that energy has to be going somewhere, right? It cannot be disappeared, right? It must be going somewhere. It must be stored in some form. It goes in displacing particle. Displacing particle does not need energy. Okay, I'm getting some answers. Yes, correct. Because kinetic energy is not increasing, right? So the energy that was given by this force, that is whatever work was done by the force, that must be stored as potential energy, right? So many of you gave the right answer. Well done, people. Okay, so that was stored as potential energy. All right, because see, we took it with a negligible velocity, right? So that its velocity never increases. So kinetic energy did not increase. So whatever energy was spent, that was stored as potential energy, right? Yes, in working against electric field, correct. If you work against electric field, then that means you are giving that much energy to the electric field. It is taking commission from you, so it is storing that energy, and that energy stored is okay, please give me a minute. I don't know what I've done. Okay, right. So let's continue. I was saying that the work done against the electric field is stored as the potential energy in the field, right? So now, if I go back and look at this equation, right, I can say that this external work, right, WEXT, this one, should actually be nothing but the increase in potential energy, delta U. That is, whatever work was done by that external force, that is now being stored, or it is used to increase the potential energy, right? So finally, we have got a relation of delta U. Let me write that, okay, separately once again. Delta U is equal to negative integration A to B F E vector, that is electric force, dot dr vector. All right. So that is delta U. Again, this was nothing but the work done by the external force. Now for delta U, I'm sure you can understand. We'll write it very easily. UB minus UA, final potential energy minus initial potential energy. All right. So this is equal to negative integration A to B. Instead of okay, never mind. I'll say that later. So Fe vector dot dr vector. Okay, so this is what we have, right? Ub minus Ua is equal to negative integration A to B Fe vector dot dr vector. All right, fine. So this formula, this is actually the the formula of potential energy difference, right? This is the difference of potential energy. If you do remember, okay, 11th standard stuff coming up, we learned that for a conservative force, the change in potential energy is always equal to the negative of the work done by the conservative force or the work done by the system. How many of you remember this? Okay, very good. Okay, I hope corona doesn't act on the memory of students, right? Okay, I see. Right. So now, if we look at this relation, well, we have got a similar relation, right? Fe vector dot dr vector means work done by the electric force, right? This is work done by the electric force, right? So now this means, because we are getting a similar relation for conservative force as we are getting for here, this definitely means that electrostatic force or Coulombian force, if you want to use such words, electrostatic force is a conservative force. All right. Okay, because we are getting a similar relation, we can make a conclusion that electrostatic force is a conservative force, and that's not a surprise, right? Because gravitational force, which was G m1 m2 by r square kind, okay, and this Coulombian force is also kq1 q2 by r square kind, so the mass is pretty much the same. So that's why electrostatic force is, of course, a conservative force, right? So now, if it's a conservative force, we can define a potential energy very well. And to define potential energy, I hope you remember that to take some potential energy, you need to specify a reference point, right? So we are going to take a reference point at infinity, right? I'm going to take the reference point at infinity, right? And we are going to say, suppose this A was infinity. Suppose the point A was at infinity. All right. So that means A is the reference. Correct? That means A is the reference, or let's say A is at infinity. So that would mean the relation that I wrote above will become UB minus U at infinite, because A is now infinite, is equal to negative integration from infinity to B Fe vector dot dr vector. Okay. Say yes if you understood this. Okay, very good. Fine, fine. I think that's clear to everybody, right? Okay, very good now. So now I hope you remember that for reference we take U infinity equal to 0, right? That is, reference potential energy is always taken as 0, right? So now this gives me the definition of potential energy. This is it. This is the definition of potential energy, right? Which potential energy? Electrostatic potential energy, right? Okay, right? This is at a point B. So if someone will ask you what's the potential energy at the point B, then you say it is negative integration infinity to B Fe vector dot dr vector. All right. So just like that, if I were to find potential energy at A, of course, instead of B, I should be writing A. Then it will be negative integration infinity to A Fe vector dot dr vector, and so on. All right. So this is a very important relation. Okay, potential energy at any point can be found using this formula. All right. Okay, does that work? So remember this or this, both are same, of course, you could choose either one, right? Remember this formula for electrostatic potential energy. Also, we have earlier seen a formula for potential energy difference, this one here, right? This is also useful, right? Okay, basically this is same as this, right? I hope you realize what I'm saying. So if you are comfortable with delta U equal to minus work done by system, it's really fine, it's more or less the same, right? Okay, so these are two important formulas that we have covered so far, right? Now I'm going to talk about definition. Okay, I'm going to say it in words. Let's continue. Do you agree that I can also write it like this? Have a look. This thing, including integration, leave the minus sign outside. Okay, leave it separate. Look at everything else. Do you realize that is nothing but the work done by the electric field or electric force in going from infinity to A? Yes? It is the work done by electric field in going from infinity to A. Okay? Right. So this exactly is the definition in words, right? So what I'm going to do is I will shamelessly copy the paragraph from the book because I don't want to write the definition here. Okay, so here is the definition. So this is it. Let's read it. You didn't understand this. Harsh, what did you not understand? The integration of Fe vector dot dr vector is work done by electric field. So that's why I've written WE instead of that. Okay, that's it. Nothing special. So this is the definition of potential energy. Potential energy of charge Q at a point in presence of field. Of course, if there is no field, there is no potential energy, right? So potential energy of a charge Q at a point in the presence of field due to any charge configuration. See, don't read the bracket. Okay, it will confuse you. Read the other things first. Potential energy of a charge Q at a point is the work done by external force, right? Is the work done by external force which is equal and opposite to the electric force, right? In bringing charge Q from infinity to that point. So this definition is saying that UA, potential energy at A, is the work done by external force, is the work done by external force, right? Okay, in bringing that charge slowly from infinity to A. But I hope you realize that because F external and Fe, they are negative of each other, because F external and Fe are negative of each other. That's why W external and We will also be exactly negative of each other. All right, I don't think anyone has any problem with these two. So that's why instead of work external, you could write UA is equal to minus WE. Well, that's exactly what we derived, right? So that is what this paragraph is telling you. But you will have to remember this paragraph, okay? It's not tough. It's just that it is equal to the work done by the external force, which is equal and opposite to electric force, right? So that speed does not increase, right? So work done by the external force to bring the charge from infinity to A or to some point. That's called potential energy. Okay. Right now we have had some questions. Sir, it is same to gravitational one. Yes, exactly, right? Okay, and another question, can we take B as reference? Okay, actually we can take any point as reference. I hope everyone remembers that reference point is actually our choice, right? But if we want a nice formula, that is K, Q1, Q2 by R, if you want this kind of simple formula, then we should take reference at infinity. Okay, otherwise you can take reference at B. The relation, the formula will be slightly different, right? What is meaning of infinity to A? Okay, again I'll just go through that. Infinity to A means the point was very far, right? Suppose, it's more like this. Here is a point A where there is some electric field, okay, right? And this is a point that is very, very far. Okay, so that is what we are calling infinity. And suppose you bring one point charge all the way from there to here. Okay, so in that process, in this process of bringing the charge, you have to do some external work, right? So that is why it is written from infinity to A. Clear? Will the syllabus be completed in time? Avinash, we don't even know what is the syllabus. I'll be very honest, right? The Gujarat government might change the syllabus any day. So they might cut chapters. I really don't know. Okay. Fine. So this is it, right? That's the formula and the definition of potential energy, right? Again, this is what you should remember. Okay, don't forget that. Now we go to the next thing. Well, that is electrostatic potential, right? From the book. Well, potential. So just like this potential energy, right? Now we are going to talk about potential only. Okay. I agree in NEET and JEE there will be full syllabus, but I don't think the next NEET is going to be before July. Okay. I don't think NEET will be before July next time. Okay. And please, biology students, please don't worry about it. Normally the NEET used to be in May, right? And we used to finish physics syllabus in December. Now we are maybe 2 months late or 3 months late, perhaps. Then I'm sure we'll definitely finish it by March. Okay, and this time you will not have your board exams like usual. I'm sure about that. So don't worry about syllabus, right? It is important to study. That's it. Okay. Fine. Potential. So what is potential, right? If you remember in 11th we studied gravitational potential. We used to perhaps write it like phi equal to minus gm by r, or I'm not so sure. We used to write v or phi. I'm not so sure though. But anyways, here also it has a similar idea, right? Definitely the symbol of potential, electrostatic potential, is V, and the easiest way to define V is potential energy divided by charge, right? Q that you are bringing. Okay. Earlier in gravitation, we defined it as U by mass. I hope you remember, right? U by L. So now this is U by charge. Okay. U by Q. Okay. So this is what is electrostatic potential. Now, if you want to define it properly, well, here we go. Uh, if you'd have a look at the definition of potential energy, right? This is the definition of potential energy. So what is potential? Quite simple. Potential is same as potential energy, but it should be for unit positive charge. I'll repeat. Potential is same as potential energy, but the only difference is instead of charge Q, it is for unit positive charge, right? So we are going to take the definition directly, right? Okay, right. It is as follows. See, U A was equal to negative integration Fe vector dot dr vector from infinity to A, right? But this potential is for a potential is for unit positive charge, right? It is for unit positive charge, unit, that is 1 positive, right? So what I'm going to do is I'm going to write this as, I don't think anyone has any problem with this step. Okay, why did I do that? So that I can put Q's value as +1. That's it. Okay, unit positive charge. So when I do that, what I'll get is called potential, right? So what I mean is, if you divide this Q on the left side, that is, I took this Q and I divided over there. All right. So UA by Q is equal to negative integration E vector dot dr vector from infinity to A. All right. So this is potential. That's it. Right. This is the potential at A. Did you understand? In short, potential means potential energy per unit charge. Potential energy per unit charge. Okay, does it need, if there is some query about potential, you can ask me. Okay, let's once take the definition, right? Okay, it's given somewhere. Yeah, here it's given in the book. Again, I'm going to copy it. Please don't blame me. You are going to have to write these definitions, okay, and remember them, and they might be asked in exam, right? Okay, so here is the definition, right? Electrostatic potential at any point in a region with electrostatic field is work done in bringing unit positive charge without acceleration from infinity to that point. Okay, V means potential. Capital V stands for potential. Okay, right. So, sir, can you explain conversion of Fe to QE? Come on, Cordell, what's so surprising? If you put a charge Q in some electric field, doesn't the charge experience a force Q into E? That's what I did, right? Okay, now take this question. Means VA equal to work external divided by Q. Yes, yes, correct. Well done. Well done. Thank you. That's right. Absolutely correct. Right. So let me put it the way Chaitya has written. You can also say that VA, that is potential at A, is the external work done on that charge Q divided by Q. Right. So that is what, in fact, this definition says. Right. It is the work done in bringing a unit positive charge. Means whatever work you are doing per unit charge. Right. Okay. So that's how you have defined the potential. Ultimately, the important formula is this. You should understand that VA is equal to negative integral or integration of E vector dot dr vector from infinity to A. All right. This infinity again is the reference. Don't forget. Just like potential energy needs a reference, similarly, potential also needs a reference. And we are taking that reference at infinity. What if electric field is not uniform? Okay, good question. But see, we are not even wondering, right? I'm writing this with integration, isn't it? That means this is the general case, right? Whether it is uniform or not, we don't have to worry, right? Integration will take care of that, right? I hope you remember we used to do integration for work if things are not uniform, right? shouldn't W external be negative? No, it will not be negative, right? W external will be positive, right? It actually, I mean, it depends on the situation, but the way I had drawn that picture, right, then it would be positive, right? If you are trying to move a positive charge opposite to a field, suppose you want to move this positive charge towards the left side in this field, then it will not happen on its own, right? You have to apply force, you have to do work, you have to spend your own energy, because electric field will try to move it or push it towards the right side. Okay, so this is a very important formula, right? This is the formula of electrostatic potential or electric potential for short. આ જે પહેલી વખત છે ને પહેલું પેજ છે ને બુકનું, એટલે બધે ઇલેક્ટ્રોસ્ટેટિક પોટેન્શિયલ લખે, પછી બે ત્રણ લાઈન બે ત્રણ ચેપ્ટર અરે બે ત્રણ પેજ જશે ને એટલે બદલી નાખશે, ઇલેક્ટ્રિક પોટેન્શિયલ કરી નાખશે. વેલ, so these are two important definitions. Now see, just like we wrote UB minus UA is equal to negative integral from A to B FE vector dot dr vector. Again, this is FE vector, right? Okay, we wrote like this. Okay, so just like this, I can also divide everything by Q. That is, I can take this Q and put it on that side in division. If I do that, I'll get UB by Q minus UA by Q is equal to negative integration A to B E vector dot dr vector. Okay, so this is finally VB minus VA, right? VB minus VA is equal to negative integration A to B E vector dot dr. This is another important formula. Everybody, make sure you remember this. All right, this is the formula of electric or electrostatic potential difference, right? Potential difference of potential, VB minus VA. V is potential, so VB minus VA, potential difference. ઓકે, અને આ જ વસ્તુ છે જેને તમે પ્રેમથી વોલ્ટેજ કહેતા હતા. શું કહેતા હતા? વોલ્ટેજ, બરાબર ને? 10th માં આવતું હતું ને વોલ્ટેજ. Sir, does it matter that charge should be placed in a field in electric potential? રમ્ય, કઈ ખબર ન પડી તારા ક્વેશ્ચનમાં. Yes, see, if there is no field, if there is no electric field, right? If there is no electric field, there is no force, right? Okay, no field, no electric force, so no potential energy. Understood? And no potential energy also means no potential. So everything is only possible if there is a field. Potential at reference will be zero. શું લાગે? Okay, Kodal is asking a question. Potential at reference. What do you think? What is the potential at reference? Yes, zero, because easy, right? Kodal, I hope now you understood. U divided by Q is V, correct? So U infinity, V infinity. But this is zero, right? Because U infinity is zero. Clear? Kodal, have you understood that? Okay, now we are going to talk about some very important points, right? Which are all related to conservative force. Okay, let's start. Potential, that is V, depends on position, right? I hope that is clear. At different place or at different position, the potential is also different, right? Okay, and it also depends on how charge, or and it depends on what kind the field is, right? Okay, that is, if there is a different type of field in uniform field at one place, the potential will be something. But suppose at the same place you change the field to be some other kind, let's say like this, okay, then the potential will change. Understood? So potential depends on at which place you are finding that potential, that is position. What I mean to say is here and here the potential will be different. All right, and it also depends on the type of field, right? So that's because the charges that create the field, suppose there are some 2 or 3 charges that are creating this field, so the potential actually depends on the charges, right, that are creating this field. So keep this in mind, that if you change the point, the potential is going to change, right? And if you change the type of field, then also the potential will change. Okay, then potential difference, potential difference, voltage, right? Potential difference or voltage between 2 points, potential difference or voltage between 2 points in electrostatic field depends only on the points, right? Not on path, right? Okay, not on path to go from A to B. Okay, so let me explain what I said here, what I've written. Suppose this is a point A and this is a point B, right? And you are supposed to take a charge, point charge, positive, negative, anything, doesn't matter, from A to B. So if you take it straight in one case, okay, sorry, if you take it straight in one case, in second case you take it like this, ગામનો આંટો મારીને રખડીને, okay. In that case, both the cases, the potential difference VB minus VA will be same, right? Potential difference VB minus VA will be same. Now this is obviously because if you look at the definition of VB minus VA, right, this is nothing but UB minus UA by Q, right? Okay, but UB minus UA is dependent on work, right? It is dependent on work, right? And because the electric force is a conservative force, right? Again, electric force is conservative, isn't it? Right? Electric force is conservative. So because it's conservative, this kind of work will not depend on path. Okay, does not depend on path. So that's why potential difference also does not depend on path. It only depends on starting point and final point. All right. So that's what this is. Potential difference between 2 points in electrostatic field depends only on the points, that is initial and final, not on the path. Okay. Now let's have a look at unit of potential energy. We'll start with that. Okay. Probably I'll answer your question after I complete this potential section. All right. I want to cover a few things about potential, right? And then we'll take your question. So unit of potential energy. What's the unit of potential energy, people? Oh, hurry up. Come on. Tell me the unit of potential energy. Okay. Volt. No. Read it carefully. Joule, right? Is that okay? It is joule, right? So that means unit of potential. Which potential? Electric or electrostatic potential, right? Electrostatic potential, right? The unit of electrostatic potential formula is V equal to U by Q. So that unit should be joule per coulomb. All right, that's the unit. Don't forget the unit. Okay, joule per coulomb, right? Unit of electrostatic potential is joule per coulomb. Okay, now, well, so we have talked about the definition of what potential energy is and what potential is. We have talked about what is the definition of potential and its units and two properties, right? One is that it is a property of position, and the second one is that it depends, potential difference depends on initial and final point, does not depend on path, right? Okay, so that is what we have learned so far. Now we're going to talk about what is the potential due to a charge. Okay, right. Before that, I have to take Sonali's question. I'm sorry. Yeah. So the question is that if we take two charges with same magnitude but opposite sign, then there will be potential. Okay. It means you are taking it like a dipole, right? Two charges with same. So in a dipole, yes, there is potential created because the two charges are not at the same point, right? Okay, so potential will be there, right? What is that potential? We'll talk about it when we talk about the dipole, right? In this chapter also we will have to study about the dipole. Next question is from Krupa. Can we write it as Vms Vb equal to work done by external force by Q? Can we write it as Vms Vb equal to work done by external force by Q? Yes, you can. Okay, yes, you can do that, right? Okay, and Coral is asking, can we write joule per coulomb as anything else? Well, actually, yes, I forgot to tell you that 1 joule per coulomb is called 1 volt, right? Named after Alexander Volta, right? Okay, so 1 joule per coulomb is called 1 volt. So this is also the unit of potential, electrostatic potential. Please remember that unit, volt, V, capital. It's a bit confusing, isn't it? Symbol of potential, V. Unit of potential, V. Right. Who will not be able to remember this? That's also V. Now, like I was saying, we are going to talk about the potential due to a point charge. Okay. See, you are going to find it very familiar. We have done it so many times. We have done it in gravitation. We have done it in first chapter. Okay. This is going to have a similar pattern. Suppose this is a positive charge, point charge Q here. Okay. And let's say over here, this is the point A, right? And far away in some distant land, there is infinity. Okay. So we want to bring some small charge Q, which is actually the test charge, right? We want to bring a test charge Q from infinity to A, right? Again, we want to bring it from infinity to A, right? And let's say somehow we have fixed this so this doesn't move, right? This is fixed. Suppose the distance of the point A from this charge is R, okay, small r as usual for distance, right? Now, you see, for simplicity, right, for simplicity of this derivation, we are going to consider that this is moving in a straight line, like this, okay, moving in a straight line, right? Is it necessary that it has to move in a straight line? No, of course not. Like earlier, just before this, I told you that potential difference does not depend on path. So that's why you could actually bring it in any way that you want, but still the result is going to be the same, right? The potential difference is the same. Okay. What is the name of this topic? Sorry, I forgot to write that. Potential due to point charge. Okay, right? So we want to find potential at A. We are going to use the definition VA is equal to negative integral E vector dot dr vector from infinity to A. All right. સીધું ઈ જ કરવાનું છે, બીજું કઈ લપ નહીં. Okay, so now this point charge Q is going to create electric field. Okay, so that electric field is going to be negative, okay, minus n infinity A kq by r square r hat. I think everyone remembers that this is the electric field due to a point charge, right? Dot dr vector is nothing but dr r hat. Okay, આ તો બધું યાદ છે ને, that we used to write position vector dr like this. Okay, I hope you all remember that. If you want to write it in radial form, you write it like this. Okay, so now we are going to do a dot product. Okay, so if we do a dot product, here, let's see what happens. Minus infinity A r hat dot r hat. What is r hat dot r hat? If you don't give me the answer, I'm going to hat you. Hurry up. What is r hat dot r hat? અવિનાશ તારા ઘરે હમણાં ફોન કરું છું, આ લેક્ચર પૂરો થાય ને એટલે કે 11 નું કંઈ જ આવડતું નથી. Okay, most of you are getting it right. બાકી બધા ભૂલી ગયા કે શું? તનય, ઓકે ફાઇન. અરે યાર બીજા લોકો આન્સર તો આપો. આ શું છે? r into r. કેમ r into r? Well, I hope you all remember that this is a unit vector. So 1 1 cos 0 આવું આવે ને. અરે યાર આવું કરવું પડે 12th માં આવીને. So this is equal to 1. Clear? અને બાકીના બધાના ઘરે ફોન આવશે આજે. So this is kq by r square dr. Clear? Okay, so this is equal to minus outside kq constant. Okay, charge is not changing. Infinity to A 1 by r square dr. Okay, I hope everyone remembers this formula. Integration x raised to n dx is equal to x raised to n plus 1 upon n plus 1. So let's use that here. The power is minus 2. Okay, so this will be r raised to minus 1 upon minus 1. Correct? Okay, r raised to minus 1 upon minus 1 because n is minus 2. So finally this becomes minus kq into this minus minus plus. Okay, now in the bracket we should put limits. R raised to minus 1 means 1 upon r. Okay, so this will become 1 by ra minus 1 by r for infinity. R means distance, don't forget that. R means distance. Okay, right? Have you understood this step? Yes or no? મેથ્સ વાળાએ કઈ બોલવાની જરૂર નથી. ઓકે ફાઇન, મેથ્સ વાળાને તો આવડવાનું જ છે. આ એમાં તો ન આવડે તો ચાલે જ નહીં. Fine. Okay, so now let's put the final step of this one. This is nothing but VA. બરાબર ને? એનો ભૂલી જતા. We were deriving VA. So VA is equal to this. But now, what is R infinity? R infinity means distance of infinity. Distance of infinity is, of course, infinity. So 1 upon infinity is 0. So here we write 0. Instead of RA, I'll just write R. I'm assuming that distance of the point A is R. Okay, as in this diagram, right? So now we go back to this. So this becomes KQ into 1 by R, or simply KQ by R. Mission accomplished. Okay, so what is this formula of? Electric potential due to point charge Q. See, everything has a different formula of potential. જેમ ઇલેક્ટ્રિક ફિલ્ડમાં અલગ અલગ આવતી કે નહીં, KQ by R square આવે, ને પછી સિગ્મા by 2 epsilon 0 આવે, ને કોક વાર કંઈક બીજું આવે, બરાબર, lambda by 2 pi epsilon 0 R, like that. So like the same thing, potential will have different formula for different cases. Okay, potential has different formula for different cases. તો ખાલી ફોર્મ્યુલા નહીં ગોખી નાખતા, આ સેન્ટેન્સ યાદ રહેવો જોઈએ. ઇલેક્ટ્રિક પોટેન્શિયલ ડ્યુ ટુ, હા એકવાર ફિગર દેખાડું છું, બરાબર. Okay, R is the distance of that point A from the charge. Okay, right. Infinity દેખાડવું હોય તો અહીંયા દેખાડ દો. Here. Okay, so we are bringing that test charge Q all the way from this to that. Okay, Harshad, is it fine? Now, yes, Priyansh, that's what I was going to say. Now we are going to the first slide because he didn't remember it. I will take your doubts, but next time. All right. Okay. In the next lecture, first of all, we will take your doubts regarding whatever we have discussed so far. ત્યાં સુધી વિચારીને રાખજો. Yes, Q is the source charge. Very good, Darshi, that's correct. Q is the source charge, right? Okay, fine. We are now going to stop. All right. So see you then. Goodbye. हाँ, एक मिनट.